the sense that we're used to thinking. But he represents definitely a trend that has become more and more pressing in the last 10 years. A trend which I saw, interestingly, confused in a recent issue of Architectural Design, devoted to his autonomous house. The issue of AD was on alternative technology. And it resulted in a lot of ADs and ATs and AHs, AHAs, and autonomous houses and alternative technologies. Well, obviously there is a large preoccupation which overlaps here, and it's still one which is having trouble finding funding and finding support. It's obviously supported in this school, but as Alex told me just a minute ago, he spends 4 months of the year not doing research on the autonomous house, but doing research on how to get grants, or getting the grants to continue research. He's been trained in the LCC School of Building in the war, during the war, and after that started or worked on a project called the Arkhorn House, which I keep getting confused with the Acorn House, which is a similar kind of project in America developed by Carl Koch. Both projects got off to a terrific start and had a great success, although failed on the point of view of hitting the mass market for which they were intended. And I hope Alex speaks a little bit about that tonight, showing perhaps some of the reasons that these projects haven't succeeded on a mass level. Since then, he's worked with architects in Cambridge, Sandy Wilson, among others. And since '71, he has been working at Cambridge University in the technical research department. Has a fund which is doing research on the autonomous house. And I think his approach is different from many of the piecemeal approaches that are going on in the same area. It tries to approach it from a general theoretical point of view before designing a specific house. Well, Alexander Pike will be talking, and afterward I think he can answer questions.
Thanks. Well, I think it's because the architect usually has an intellect of such a diverging nature that the word architecture has become imbued with a wide variety of meanings and interpretations. So an invitation to an architect to speak on architecture can be very much like a blind date. You don't know quite what to expect, and you hope it'll turn out all right, but you must be prepared for almost anything. Now, I'd like to confine myself to a fairly normal interpretation of the word, and I feel that my own self-questioning approach is the one that's adopted by most of us, and I imagine that the questions I ask are those that we've all ask ourselves at one time or another. For example, in housing, which is a world problem, why have we been unable to solve the problem of providing cheap houses in sufficient quantities? We've been able to provide most of the luxuries of life, things like cars, washing machines, etc., in great abundance and at quite reasonable cost, yet the adequate provision of shelter, one of the prime essentials, still eludes us. Perhaps if we could have the first slide now. Now, this is Lima, and the space you see here between those sort of two doors and the space about 2.5, the most, say 3 meters deep, houses a family of 5 people, totally. That's another one that houses 5 people. Incredible as it may seem. Now, after all, a lot of the world is living like this. Now, Now, most architects, whatever their main area of interest or specialization, find a challenge and a fascination in the design of the individual house and its problems. But this is often a concern for the creation of an individual gem to remain as a monument to its designer. And it's perhaps this preoccupation with the creation of monuments, this big A architecture, that's blinded so many architects to the problem of the small a architecture. That is the real difficulty of providing a sufficient quantity of the essential sorts of accommodation and still introducing architecture into the scheme. Now, similarly, on this point of questions, why, when so much effort has been expended on planning with a very... sorry, that's just a blank, that's all right. We've got a high... just to avoid you staring at the same thing for too long a period of time. We've got this very high ratio of architects and planners, and we have what has been described as the best planning acts in the world. Why have we arrived at a situation where the average member of the public is really quite dismayed by much of the newer work that he sees around him? All of the built environment of the last 30 years has been built, with very few exceptions, with the agreement of planners and planning committees. Yet, how often can we actually cite examples where the results of these approvals have created something better than the best examples of the uncontrolled and randomly planned towns and villages throughout the country? In a strange way, some of those barriadas in Lima are much more interesting than many of our sophisticated housing schemes, although they're produced at absolute minimum levels economically. Now, one of our big difficulties, of course, is in keeping abreast of this bewildering rate of change, and it's perhaps this rate of change which accounts for that sad phenomenon by which those who are perhaps bright stars in architecture during their peak years, in say their early 30s, can become quite passé and even discredited by students when they reach their 50s. Now, for the public, this rate of change results in their seeing the environment to which they've become very accustomed altering at an alarming rate. And there are many complaints, actually, from the public that the quality of the new work is not as good as that which it's replaced. So the architect finds himself in a dilemma. 15 years ago, or maybe even less, it seemed that technology had reached the point where it could provide all our needs cheaply and with so little effort that one of the real emerging problems at that time seemed to be how people would be able to fill their leisure time. And we were considering, without perhaps realizing the implications, the high energy buildings, factory manufactured structures for mass production, throwaway buildings with a built-in obsolescence factor, and things like all plastics houses, adopting what we now call a hard technology in general. Now we must investigate labor-intensive buildings, utilizing renewable resources, demanding minimum inputs of energy during manufacture, construction, and occupation, and built to give a long life expectancy, but still providing sufficient flexibility for choice of a range of different lifestyles, styles, and different sorts of use during its lifetime. Also, we're reassessing the standard economic theories and those possibilities for growth and expansion that were formerly taken for granted are being very seriously questioned by economists such as Schumacher and Michan. They're providing very strong arguments against the old theories. So we live in an age of anomalies. This is a century in which we are, as a race, have produced and amassed an unprecedented amount of knowledge and technical expertise, but it seems that we've learned at such a rapid rate that we're either unable to assimilate this knowledge that we've gained and then forget much of it, or we misapply it and blame the resulting disasters on the technology that we ourselves have created and haven't had the wisdom to use well. Now, we reach a position, for example, whereas in 1921 Henry Ford was able to produce 1.25 million cars in that 1 year, very cheaply indeed, and for that matter, paying very good wages to his workers. We're now, more than 50 years later, with 50 years of progress, unable to produce cars in the same quantities and at economic prices. Just let's look at some of these. Sorry, we're going back. These figures I find very interesting because they show the growth of, well, you might say the growth of mass production. This shows the period when Ford started to really produce cars in high quantity, where his annual sales started to shoot up in about 1910, and his costs, for those at the back who may not be able to see these figures, range from $950 at the peak point down to $360 in 1921, and it corresponds so closely with the output figures. And interestingly enough, here he created riots when he raised the minimum wage from $2 to $5 a day, which was an incredible move then, and didn't make him very popular with his competitors. Now, that's the sort of anomaly we face. And in architecture, we have more than our share of these anomalies. For example, during the 4 years preceding the Second World War, our output of housing averaged 358,000 units a year. Well, that's a rate we've never achieved since that point, despite a larger labor force, increased site mechanization, improved organizational techniques, and larger supplies of materials. Again, during that point, the temporary housing program of 1944 was introduced, and mass-produced houses were being turned out at a rate of 1 every 12 minutes from the factory. And they could, under pressure, be erected by 8 men in 7 hours. Perhaps we can have a look at these things. This is the plan of the Archon house. It had this really quite efficient heart unit, and in many ways I don't think as a heart unit it's been bettered since then. It has this open stove here with a back boiler which gave full warm air, ducted warm air heating to the whole house. A house produced under pressure, obviously, under wartime conditions with shortages of materials. But although it was intended only for 10-year life, some people are still living in these and prefer them despite offers and even pressure from local authorities to accept council houses. The appearance, well, it's hard to judge because the pressures and the problems were so great that the amazing thing wasn't that they don't look all they could be. The amazing thing really was that they were able to be provided at all. But again, even the fastest rate of production since then hasn't exceeded that sort of output. We've explored almost every avenue for the prefabrication of houses, but despite all the work that's been carried out in this area of study, we've not been able to prove conclusively that this method of building is either cheaper or better or even faster than conventional building. And yet we had the magnificent precedent in this country of the Crystal Palace as a pointer for the future. This was an immense building of 33 million cubic feet capacity, erected, by the way, at a cost of a penny a cubic foot, and with working drawings completed in 7 weeks and manufactured and assembled entirely in 9 months. I find that quite incredible. And I suppose any architect these days who has to deal with the problems that we face will also find it rather interesting. Now, although this building appears to us to be an obvious candidate for standardization, we must remember that considered in the architectural climate of the day, it wasn't. And the truly significant features of Paxton design were not merely the consideration given to the function and the formal layout of the building, but also a comprehensive attitude towards construction, materials, methods of fabrication, economics of production, and simplicity and speed of erection. He had all those factors pretty well buttoned up. And it seems sad to me that although the building inspired other great works using the same materials, the underlying principles of standardization were largely ignored, and they remained pretty well dormant, I think, for perhaps 70 years. And it's even more sad that the more recent application of these principles has produced, in the majority of cases, very sterile and monotonous building. And so it's ironic that after all the effort that has been applied in these directions in the past 30 or 40 years, we find ourselves facing a future in which the capability for machine production may be very limited. And of course this is prompted by our belated awareness of the way in which the supplies of the Earth's materials are dwindling, and the dawning knowledge that our almost infinite capacity for reproducing ourselves and our constantly increasing demands on reserves doesn't correspond in any way with the finite nature of the resources we need to sustain ourselves. You may have seen these sorts of charts before, but I think they're very mollifying. We should perhaps look at them more often. Considering these materials, this is from an article in the Scientific American, by the way. Now things like chromium, nickel, molybdenum, tungsten are, manganese as well, really quite vital materials to our present way of life, because they are needed for the alloys for machine tools steel. And again, for those people who can't see the scales, this is 1980, this is the year 2000. It's quite clear that when those reserves fail or start to fail, we will have quite serious difficulty, and unless technology comes up with some miracle in preserving the way of life we most of us enjoy at the moment, because our capacity for producing things in high quantity at reasonable cost depends to a very large extent on these sorts of metals. Now, on this question of reserves, it's too easy for us to claim that we in this country are not affected, and that with a population doubling rate of 117 years, we need not concern ourselves with those countries which are doubling, for example, their population every 13 years. Well, I feel that we are morally involved in this situation, and apart from that, I think there can be no doubt that we'll eventually become heavily involved, whether we like it or not, both physically and economically. Now, the means by which we can provide a significant help with the problems of the underdeveloped countries is not clear. As an example of this, you're, I'm sure, familiar with these expanded polyurethane foam houses, which were intended and used for sort of disaster areas to provide instant housing. Now, this is really a product of high technology, the Western world, and seems quite a feasible solution to the problem. It's about 4 inches of expanded polyurethane. Now, unfortunately, you see, it's terribly easily cut with a knife, and in this particular case I show here, it's the back of the one you saw previously. Whilst the occupants had gone to market over a weekend to sell their wares, a neighbour just came along with a knife and cut the back out of his house to put onto his own. It's not an absolute solution to the problem. Now, apart from those sorts of things, I think there can be no doubt that the difficulties of people in those countries are aggravated by the distribution of their swelling population. And it's paradoxical that the countries which have the most severe problems in this respect often have extremely low overall densities of population, but they cluster together at very high densities for reasons which we can all understand, but nevertheless happen. Now, of all the resources with which we've become concerned, it's energy which has become the most obsessional preoccupation. And although this was one of the basic stimuli behind the original concept of the autonomous house at Cambridge in 1970, I can't claim any prophetic capability in this respect. This house, together with many others, has been termed a house of the future. Now, this is a phrase which is obviously received rather cynically by architects who are well aware that every house designed today is a house of the future, unless it's a throwaway thing for a limited period. It's probably going to be around for at least 60 years, and more likely now, in the light of current events, perhaps 100 years. So we must think of every house as a house of the future. We can't draw distinctions. But anyway, one of the basic considerations at the commencement of this project was the obvious fact that the more easily won sources of energy, materials, food and water would deplete at an increasing rate with the passage of time, and that energy would become the key factor, and that each newly found supply of fossil fuel would be voraciously consumed by the constantly increasing demands of an affluent society. Now these you may have seen before, but again, items along here on the right are all domestic facilities which I think almost without exception carry some energy implication. The green line is just the 50% ownership. Well, now it's clear that many of these items are already soaring up towards the 100% ownership, and even those below the line have a very steep inclination. So they're the sort of extra demands that we're all making in terms of energy by our use of, well, all the things that we enjoy having, like record players, refrigerators, and that sort of thing. The other point to consider, energy basically, now these are, I think, are probably all familiar to you, these sorts of graphs. We've got a world population increase which looks as though it's becoming exponential. A per capita consumption of energy which is rising at a very steep rate. If we aggregate these two curves into the one on the right, we get some quite startling figures, because this vertical scale is in kilowatt hours per day. That scale is in kilowatt hours per day times 10 to the 10th, which is really a massive sort of curve if they were translated onto the same sort of vertical scales. Now, the early promise of cheap and plentiful nuclear power has faded as the problems proliferate, and the gradual build-up of nuclear waste, with the probability of insuperable difficulties of containment, must, I think, surely stir the public conscience against leaving this as an unbearable burden in terms of a legacy for dozens or maybe hundreds of future generations. There was another factor which seemed important at the time we started work on the project, and that was that in a future faced with shortages, the cost and losses involved in distributing services such as electricity, gas, water, and sewage disposal, already deserving much closer attention than they receive, incidentally, would assume much greater importance. It seemed that the economic viability of network services had become questionable, and their influence on city growth perhaps much more significant than was generally supposed, and probably forcing us to accept that accretive form of expansion which has now become standard, even if it's not necessarily desirable. And it seems that this pattern of urban growth produces those concentrations of population which aggravate transport problems, pollution, land values, crime rates, other sorts of social disorders, and in fact having a disastrous effect on the centres of many of our towns and cities in a physical way. And it's also quite expensive. When, again, these scales are city populations of 200,000 up to a million. When you start plotting local tax revenue or rates for living in those cities of those sizes, you see that it becomes more expensive to live in the larger city. Well, it's a fairly obvious thing, but it can be shown there's a fairly close correlation there, because the whole infrastructure required for the larger city demands a different sort of financing and economics. We also, at that outset point, apart from those considerations, took the view that an impending leveling of standards, and in fact in many cases reductions of standards, would for many people militate towards a lifestyle which might be intolerably different unless we planned for measures which increased self-sufficiency and self-determination. So from that point, the concept of an autonomous house, freed completely from connections to centralized services, seeks to make a contribution towards solutions to some of those problems that I've just outlined. Now, the general principles of such a house are widely documented, but much of the written matter on the subject is prompted by the rather poetic or romantic ideal of the self-sufficient house, and consequently many proposals are based on instinct and emotion, and the motives and objectives behind the studies vary very considerably. Now, unlike most of the projects emerging in this subject area, the Cambridge House seeks to achieve total autonomy. And this is an objective which is being criticized in some quarters as being overambitious. And the critics claim that the supplementation of conventional inputs by ambient energy sources is as much as can be hoped for, and that the additional effort required to extend beyond this point to full self-sufficiency would not be cost-effective. So as some misunderstandings may have arisen on this point, I think I should try to clarify this aspect of the project. I feel that one of the principal arguments in favor of autonomy, or more correctly now, autarky, because I've been corrected on this term, autonomous, because this means self-governing, and we're certainly not aiming for a house which rules itself. This is not going to be a machine for living in which decides what it should do, even if it's against the wishes of the occupants. The more correct term, I gather, is autarky, which means sufficient unto itself. So the baby has got a new name. Anyway, one of the principal arguments in favor of autarky is for the planning freedom it might provide, giving us a range of options for alternative planning strategies that we're currently unable to explore because we're limited to the constraints very often of the existing networks or the constraints that we impose by the provisions of new ones. We've not been able to prove that high-density housing development is either socially desirable or economically justifiable. Yet a combination of high land values and reliance on the network system for services forces us to maintain a planning principle which is quite obviously viewed opprobriously by a large section of the community. Now, it seems that self-sufficient housing might provide the basis for the economic development of very low density housing, but obviously much more work needs to be done on the evaluation of transportation costs and their implications for energy expenditure, and these, and also studies on the overall energy flows in urban locations, on which hardly any work has been done, are necessary before useful discussions can take place on the relative merits of centralized or decentralized developments. Now, another consideration is the problem associated with our dependency on centralized services. We're all aware that strikes, power cuts, and severe weather conditions can be sharp reminders that once these services fail, then even the most highly serviced house can suddenly become very primitive. In a strange way, of course, the most highly serviced house becomes the most primitive. And in those circumstances, the provident and conscientious energy savers suffer the same fate as the squanderers, and overloads caused by one group of the community restrict facilities for the other. Now, it seems that the fully self-sufficient house could provide the means by which the individual householder could achieve a measure of independence and self-determination, which is so often sadly lacking in modern life, I think, in society, where he would be affected by the results of his own actions rather than of those taken by others, and that he could be confident that he could make decisions that would not be vitiated by other members of the community. Now, this is a freedom of action that's currently enjoyed by comparatively few individuals, most of whom have to sacrifice standards of amenity. They have to go and live in a bothy somewhere, and are forced to endure a rather Spartan existence. Now, if we accept large-scale developments such as new towns, it seems that the pattern of city growth is very much dependent on the form laid down by services networks, so that future growth, as I say, becomes accretive on the edges of the existing settlements. Now, we attempt to justify these networks by this fondly held belief that centralized generation, collection, and distribution of services is the most economical method. And as these economical considerations form the original basis for the existence of the networks, we felt at the outset it was worth studying these costs in some detail. We found some quite interesting and surprising figures. The per capita cost of central plant, for example, for those of you who can't see the scales, population scales here, 10, 100,000, 10,000, 100,000. Now, we found that obviously annual per capita cost of central plant increased as the settlement size decreased. And that wasn't surprising. But what was surprising was the comparatively small differential in costs between large and small settlements. Now, these figures are, we can never keep the cost scales up to date these days. These are 1973 figures, but you can see the sorts of scale we're talking about. Now, in that case, the annual per capita costs were £18 per person per annum for a population of 10,000, and just under double that, £35 per person per annum, for a population of 100. Now, the distribution costs follow a similar pattern, where here we're talking about densities per hectare from 10 to 100. And again, with very small differences in costs for large differences in density. At that time, £3 per person per annum for 100 persons the hectare, and only £10 per person per annum if you reduce the density to 10 persons per hectare. Another interesting point was when we amalgamate land and services cost. These are the costs of the respective services: electricity, gas, water, telephone, refuse, etc., sewerage, which increase as the distance from the central plant increases. But at the same time, land costs drop quite radically with that distance from the central point. So by amalgamating these sets of values, we get a total cost of services plus land which drops as you get further from the center. And this point here, which is showing a rise beyond a certain distance, is really a theoretical level, because it's at that point usually where the services have become so attenuated and so expensive to run out any further filaments that they are no longer provided. Now also we find that the per capita costs for transmission increase rapidly as the population drops to very low levels, and eventually here at a population of 3, for example, equates to the cost of on-site provision of services for water, waste and power. Now, moving on from that point, we've carried out sufficient work to show that such a completely self-sufficient house is theoretically possible, and to justify the construction of an experimental prototype on which this performance can be monitored and the opinions of the occupants sought. Now, the objective in this case is not to provide a house which merely satisfies the bare needs for survival, but actually to provide the level of amenity that is currently enjoyed by most householders. Now, I know in some areas this objective is not popular, but on the other hand, I feel it's right to provide, or to spend whatever money we have in research on this subject, to provide for the larger section of the community. And I think this is the average person who expects a certain level and would be greatly disturbed by dropping to a much lower standard. Now, it seems that to achieve this, it'll be necessary to employ a strategy which not only explores the maximum possible efficiency from the limited inputs that we've got available, but also matches this by a reduction in demand. And because of the reasons I've just stated, this should be affected not by restrictions on a mode of life, but by improving the efficiency of appliances and the equipment in the home and reducing wastage. So this indicates a very thorough re-examination of all the conventional performance standards for components and elements, and an examination also of the functional requirements normally postulated, together with a much more rigorous analysis of the facilities provided and the way in which we use them than we would do in the design of a normal house. Now, again, I'm sorry, this diagram tries to show too much, and in doing so shows very little at all. But what it does show is that you can analyze the functions of a house into a number of circuits, and these circuits occur in one way or another in every house. They are not all closed circuits in a conventional house, and we usually find there are spurs off those circuits which are represented as waste. Now, what we're attempting to do in this house is to take those spurs out of the circuits and either feed them back in some way into that circuit or into another circuit, so that wastage is eliminated, or at least reduced to the absolute minimum. And what I'd like to say here is that the proposed house at the moment is not intended as a stereotype or even as a definitive solution, but it's merely a framework for a number of experiments that have been formulated during the theoretical phases of the work. And the form, as it stands at the moment, has been derived from, derived from a number of considerations. It is capable of collecting heat both passively through this glazing on the south and on the west elevations, and actively through the solar collectors at the upper level on the south side and in various levels on the west. And these glazing collector elements will be interchangeable, and that'll enable the theoretical optimum proportions derived from design simulation to be tested experimentally. Now, internally, flexibility can be provided, I'm sorry this isn't an awfully good slide, by a series of partitions, so that the internal spaces can be arranged to give variable volumes and areas for different domestic functions, and these can be adjusted to changing activity patterns and climatic conditions experienced throughout the year. This is living area, and same sort of thing in the kitchen dining area. The range of subdivision of living space within the overall envelope will enable us to change the ratios between the surface areas and the volumes of the habitable zones, and the total surface area of the collector, and these ratios can be changed disproportionately. This aims to overcome some of the problems generated in conventional designs, in which you get mutually incompatible variables. The limited inputs available in terms of solar energy, for example, militate towards small volumes for occupation, for space heating, and minimum surface areas for heat loss. But, of course, due to those limited inputs, or to the low density of those inputs, it demands large areas for solar collectors. So, in other words, you need two different sizes of external wall, a large one for collector surface and a small one for reducing the volume of the house. Now, the basic minimum area of the house before variation is approximately 65 square meters. That's this zone on the left. It's a conventional plan, with the exception, of course, that it's very minimal area for a two-bedroom house. That accommodations on 2 floors, and it's envisaged that this area could provide acceptable living standards for those few periods during the year when exceptionally low ambient temperatures would demand the use of this minimum volume. Because after all, it's not that frequently that we get the really bad sub-zero temperatures. I know that's a wrong point in time to say this at the moment with this cold spell, but fortunately it's not that often. Now, under those conditions, the occupants would have the option of forfeiting some of their space standards to maintain thermal comfort and to conserve their house energy reserves. And of course this practice is frequently attempted, I think, during inclement weather by many householders in conventionally designed houses. And of course it was the subject of government exhortations during the winter of 73-74. But it does give rise to difficulties due to those severe contrasts of temperature in different room spaces. Now, opposed to that occupation of a very small area for comparatively few days in the year, for most of the year, certainly from early spring to late autumn, and possibly on many sunny days during a winter period, it's anticipated that the additional space within the overall volume, that's this area on the right, could be used for living purposes, and that would give an overall floor area to the house of 111 square meters. That's considerably larger than we would expect from the conventional space standards for a 4-person house. And I think it would adequately compensate for the restrictions during the winter period. The point here is, I think, considering the fact that many families expend a lot of time and effort on nurturing a garden which they can use to the fullest effect for, shall we say, sunbathing or outdoor meals and that sort of thing, on disappointingly few days throughout the summer, this sort of enclosed garden area does provide a space which would enable the occupants to enjoy some of the effects of outdoor living without having to endure the rigours of a normal British summer. So the first floor plan is one, again, very conventional, tightly planned in this zone, but with these bedrooms in fact forming galleries overlooking the space in the garden area, so that we get a section which shows this very much reduced living space here, and furthermore with low ceiling heights, substandard illegal ceiling heights incidentally, about 2 meters, which again is all part of our approach to try to reduce the volume during those very severe periods, because we're not talking here about a house where when the temperatures drop to very low levels, you've got mains services you can fall back on and switch on a few more bars of electric heaters. We wouldn't have that facility. So during the winter we'd be relying on the heat that we've stored in this thermal battery here from solar radiation collected mainly during the summer, with a bit of boost from winter sunshine, for which this wall is sloped to the optimum to catch that sunshine. So we're looking for everything we can get in terms of saving of energy, and volume does count quite a lot. Now, you're probably familiar with the estimates of the percentage of energy demands due on space heating, and these vary from 61% to 75% of the total. Now, as the density of usage of this heating normally is very low, about 50 or 100 watts a square meter of floor area, and equates very well with the average intensity of solar energy flux in this country at about 100 watts per square meter, continuous that is, then this provides an obvious choice for the purpose. There are, however, problems. The vagaries of our climate pose problems that have not yet yielded solutions suitable for universal application for solar collectors. So we face a problem here where certain manufacturers may claim, say, a 53% or 55% in some cases efficiency for their solar collectors. Unfortunately, it's our solar radiation which isn't very efficient. It's certainly not as continuous as we know as climates like Texas or Arizona or even Washington. We get a lot of intermittent cloud cover, and the point is we don't know enough about this. We don't have sufficient meteorological data, although records are kept of solar radiation on 33 sites throughout the country. They're mainly for horizontal surfaces, and only in a few locations are they for vertical surfaces also. And although we can arrive at calculated figures for inclined surfaces, we're still left with very large voids in our knowledge of the response of solar collectors, particularly in relation to the fluctuations that are produced in this country by short-term cloud cover. And so this makes predictions of the efficiency of different types of collector that have been devised and used in other countries very difficult. And also, of course, it means that to find out what the efficiencies are in this country, you need a lot of quite heavy instrumentation to discover what efficiencies you're actually getting. It's very simple to wait until the sun shines and then see what sort of efficiency you're getting from your collector, but to have the collector in continuous use where the circumstances might in some cases be that we're losing more heat from the collector during the period of cloud cover than we have gained during direct radiation, makes it very difficult. And also the differences in values for efficiencies that have been measured by other workers in this field leave us a little perplexed. For example, Chinnery in South Africa has done a lot of work on collectors of different types, and using an aluminium tube-in strip form of collector, fairly sophisticated type, similar to the Milton Keynes collector, he shows an efficiency of 57%. But he shows an efficiency of 53.5% from ordinary black polythene piping, where obviously the cost difference between those two types is vastly different, even if there is a difference in life expectancy. I think I need not point out to you the problems at the moment where the energy crisis has provided a sort of incentive for extensive studies on the subject of solar collectors, but it's also stimulated commercial activity based on that public interest. And there are a number of manufacturers now producing collectors as an extension to their range of standard products of one form or another. And the high cost of these collectors, combined in some instances with very low efficiency, may prove to be a sad disappointment to those enthusiasts who've decided to have them installed, and this may consequently damage the movement very much, I fear, by hardening the market against any improved forms of collector or cheaper forms of collector, which is the same thing, that may be devised in the future. Now, on this house, our computer program, we've used a simulation program to try to save money on full-scale experiments. So we've taken the metadata from Q on their tapes, full metadata for the past 12 years, so that we can feed them into our program to find out how the building would have performed if it had been subjected to the total weather during that period. And this, I think, is a very important thing, because one of our problems is we never know when we're going to get exceptional weather. The very severe winter or the very bad summer, or for that matter the very good summer. We have to take the figures over a long period of time if we're going to arrive at any sort of conclusions that can be presented with confidence as a house that's going to work. But anyway, our program confirms the finding of other workers in this field that the short-term storage of solar energy carries a very high risk of failure in a totally autonomous situation in this country. And the interseasonal storage of energy is the only satisfactory solution, and this was suggested more than 20 years ago by Hooper in Canada in his proposal for a solar heated house. And in that example, the energy was collected in a 56 square meter tank. 170 square meter tank from 56 square meters of collector. That meant the tank was pretty well the same size as the house, I think. Now, in the Cambridge proposal, the heat store will be a tank of 40 cubic meters. That's the overall capacity, and it's compartmented to permit experiments varying the volume and type of heat storage medium. Now, in our attempts to derive the maximum benefit from the energy fluxes of the British climate and to devise a fully integrated system, it's obviously been necessary to consider the use of wind power for generating electricity. Sorry, I should have one in there. Something's gone out of... Oh, I beg your pardon. We should have shown this before. This is merely to show the position of the sliding, heavily insulated screens and pivoting shutters up here